Hey, how's it going, guys? Today we're going through integration, a very basic introduction of integration, but really important to understand the fundamentals when it comes to integration, and specifically for this video, how it actually relates to differentiation, because integration is actually very closely related to differentiation. And we're just going to illustrate that quickly through this quick flow diagram. So we should know what integration kind of means through just understanding it as the backwards of differentiation. So if I have a function and I get the derivative, that process is called differentiation. We've already learned that, pretty basic process. You just apply the rules and that gives you our derivative. We know derivative has a bunch of synonyms, differentiation, derivation, rate of change, all these types of things, gradient function. But just know that if you go from a function to its derivative, we call that differentiation. That's kind of the commonly used term that we use. Now, to go backwards from a derivative back to its original function, we actually call it integration. So integration is just the opposite of differentiation. That's a really important thing that you need to understand. And it's something that, you get used to as you go, and you notice that the rules are even backwards as well, but we kind of learn it as a separate thing, just to make sure that you understand them respectively and individually. And then we combine them together to kind of bring them into examples where you need to understand that one is just the opposite of the other. Now we're going to illustrate kind of how integration works and what the flaws are of integration compared to differentiation with a quick example. So we see here we have two different functions. They're kind of similar. The first one is f of x is equal to x squared plus 1. Now, if we find the derivative of this, what we do is we just use that power rule. We multiply down by that power, and then we minus the power by 1. So in this case, x squared becomes 2x because the 2 goes out the front, and then 2 minus 1 becomes 1, which is the new power. The constant of 1 has no effect on our derivative, so that just is completely ignored. Now, if we do exactly the same process for g of x, the derivative of g of x is going to equal x squared becomes 2x, same for this one, and again, the constant is ignored. So we actually get two of the same derivatives for f dash of x and g dash of x. They're actually the same from two different functions. And that's kind of a confusing concept, right? Because if we have we start off with two different functions, right? And we convert to the same derivative. So if we were doing integration and we're going backwards of differentiation, what function would we get to? So let's say we started with f dash of x is equal to 2x, or just any rule is equal to 2x. Do we go to x squared plus 1? Do we go to x squared minus 2? Do we go to a different constant? That's kind of the problem with integration. It's that you're missing that constant of integration. That's actually what we call it. The term is called constant of integration. And that pops up whenever we find the integral of something, or the antiderivative of something. It's the synonym of the same term. Now, this constant of integration always comes up, and I'm just going to try and do a smooth transition here. Cool. I've prepared this different function name. I didn't want to confuse it with f of x and g of x. We've got h dash of x here is equal to 2x. Now, if we were trying to find the integral of h dash of x, would just give us h of x back again. 2x becomes x squared. We kind of illustrated that through differentiation through the previous example, but we don't know what the constant is. It could be plus 1, it could be minus 2 like the previous examples, it could be something completely different. Now, in general, we just leave it as c. If you're not given any other information, you leave it as plus c, and you only find it if you're given that extra information. So what I mean by extra piece of information, it's usually a point that lies on the curve. So for example, h of 1 is equal to 4. This is a point, essentially 1, 4 that lies on the curve. So if I substitute those x and y values into my function, what I get is 4 is equal to 1 squared plus c. Therefore, c is equal to 3. So therefore, I actually know my full function as h of x is equal to x squared plus 3. And that's my extra piece of information that I need to find my full function. Before we learn something, it's also really important to understand where we actually use it. So there's two main applications for integration. The first one I've kind of already mentioned before, and this is kind of maybe a bit of an example of when we would use it. Let's say if we have the rate of change of something and we want to get back to our original model. So let's say if we have a model for, let's say, the rate of change of population in a certain country. If we integrate that model, that's actually just going to give us the population numbers. And again, it's just the opposite of differentiation. I'm going to reiterate that in every single video, and it might sound like a broken record, but it's really important to understand that it's just the opposite of differentiation. So for example, if you had the population model and you differentiated that, you'd get the rate of change of population. So integration just takes us back from the rate of change to the original number. Now here's the second application that is really important, really fundamental for integration, and it's something that it's not really covered in differentiation, because it's not really, you can't really do much about it in differentiation. But using integration, we can actually find the area underneath the curve. So this curve here is f of x. You don't have to worry about how the algebra works right now, but just know that if you integrate a function and you substitute in certain bounds, let's say this bound is a, this bound is b, it would actually give us the area that's underneath the curve and bound by the x-axis. Really cool application, and really important application when it comes to understanding integration as well.